this problem is asking us to estimate the value of this definite integral. Since our knowledge of integrals right now is still very basic, we still don't have the full set of tools available to evaluate integrals in an easy way. The way that I think we can try to pretty much approximate the value of this integral is by using the second part of the comparison test for integrals. I have it right here. We have this property saying that if f of x is bounded by little m and big M, and if that is the case for every x in the interval ab, then the definite integral is going to be bounded by the small rectangle whose area is little m times b minus a, in that larger rectangle whose area is big M times b minus a. And in this way, I'll have a decent approximation of the value of the definite integral. Well, in this case, of this definite integral right here. I want to find out a little bit more about my function, about how it behaves in the interval 0 to 1. So here, the function in question is f of x equals e to the negative x squared, and we are going to be working on the closed interval from 0 to 1. I want to see what happens. Well, how is the function behaving in this interval? So in order to do that, let's go ahead and find the derivative. So f prime of x is going to be equal to e to the negative x squared times negative 2x, which is going to be equal to negative 2x times e to the negative x squared. So re-expressing this in the following way, negative 2x divided by e to the x squared hopefully will allow me to do an analysis of what is happening here. Let me go ahead and find the critical points. So in order to find critical points, I want to figure out for which values of x will f prime of x is equal to 0, or f prime of x is undefined. And immediately, if I look at the denominator of my derivative, e to the x squared is never equal to 0. In fact, the entire expression is defined for all x values. So then that means that this over here never happens. F prime of x is always defined. I'm going to make a note over here. F prime of x is always defined in our desired interval, in the interval from 0 to 1. I'm just going to be focusing on that interval right now. Then, where is f prime of x equal to 0? So let's do this case over here. F prime of x is equal to 0 when the numerator is equal to 0. When negative 2x is equal to 0, that means when x is equal to 0. And then I'm going to go ahead and do the first derivative test. So that will be our third approach here. And the reason why I want to analyze the first derivative is because I want to find out whether my function is increasing or decreasing in the interval from 0 to 1. This is going to be very valuable information. So let's go ahead and do that as we did before. In previous chapters, we're going to draw the number line right here. This is going to be f prime of x. I am going to place 0 on the left, 0 on the right. I don't care what happens outside of my of 0 and 1. I only care about what happens inside of 0 and 1. That's where I want to analyze the derivative. We're going to write down the derivative here on top. That will be negative 2x divided by e to the x squared. And then let's look at the numbers between 0 and 1. They're all positive. The denominator of my derivative is e to the x squared, which is always going to be positive. So the sign of the derivative will completely depend on negative 2x. Since all x values between 0 and 1 are positive, if I plug in a positive value for x in the derivative, the numerator is going to be negative, and a negative over a positive is negative. So I know that the first derivative will be negative in that interval. That is telling me that f prime of x then is less than 0, which means that the function f of x is decreasing in the interval from 0 to 1. So I already know that my function is decreasing in that interval. So then if it is decreasing, then that means immediately that f of 0 will have to be greater than f of 1. Let's go ahead and find those values. What is f of 0? F of 0 is going to be equal to e to the 0, which is going to give us 1. And f of 1 is going to be equal to e to the negative 1, which is going to be equal to 1 over e. So since the function is decreasing, then this is telling me that 1 is going to be an absolute maximum, and 1 over e is going to be an absolute minimum in that interval. The function is decreasing in that interval. So then 1 is going to be the absolute maximum, and 1 over e is going to be the absolute minimum value. So I can now say that the function, in other words, I can say that e to the negative x squared is going to be bounded by 1 over e and e. In other words, e to the negative x squared is going to be greater or equal than 1 over e, and is going to be less or equal than 1. I can perfectly say that. And that's going to happen, it's going to always be true in the interval 0 to 1. So then, practically then, what I have is the following. I have that my function is bounded between 1 over e and 1, and this beautifully matches the condition of my comparison test for integrals. That means that I can conclude, or that implies that the integral from 0 to 1 of e to the negative x squared is going to be less or equal than 1 times b minus a, so 1 minus 0, and is going to be greater or equal than 1 over e times 1 minus 0. I want you to notice that 1 over e plays the role of little m, and 1 plays the role of big M. So then this inequality follows nicely. So this is the same thing as saying 1 minus 0 is 1. So 1 divided by e is less or equal than the integral from 0 to 1 e to the negative x squared dx. By the way, if you notice, I forgot here to insert dx. All right, continuing, and this is less or equal than 1. So notice now that we found a bound for the integral. Now we know that our integral is going to be a number that is between 1 over e and 1. And 1 over e is approximately 0.37. So if I write 0.37, what I have is the following. I have that my definite integral is going to be a number between 0.37 and 1. And this is the way that I can have a reasonable approximation of my integral. I don't know exactly what the value is going to be, but I know that it's going to be a value between 1 and 0.37. Notice that here on the left, I've inserted the piece of the function that happens to be between 0 and 1. And indeed, you can notice how the graph it's decreasing in that interval. And in that interval, the absolute maximum happens to be 1. And the absolute minimum happens to be at around here, this value slightly above 0, which is precisely 1 over e. So everything, all the algebra over here matches beautifully with the graph that we are observing. And one final comment that I want to make here in order to completely finalize this discussion is just to briefly mention that all of the functions that I'm dealing with here are integrable. I mean, this is part of the conditions of these comparison properties. In fact, I should have argued integrability earlier on in my solution. All right, so if I am looking at my constant functions, 1 over e and 1, those functions, because they are constant, they are continuous. And if a function is continuous, it is integrable in that interval. And when I look at e to the negative x squared, that function also, I mean, e to any exponent as a function is always going to be continuous. So if e to the negative x squared is continuous in the closed interval 0, 1, it is also integrable. So all of the conditions of my properties are satisfied. So therefore, the conclusion is true. In this example, they're asking us to prove the following inequality. The integral, the definite integral from 1 to 4 of 1 over x squared dx is less or equal than the definite integral from 1 to 4 of 1 over x dx. It may be useful to think about the comparison test for integrals. I'm thinking of the first one. If f of x is less or equal than g of x for all x in AB, and if I know that f and g are integrable in AB, then the definite integral from a to b of f is less or equal than the definite integral from a to b of g of x. I feel that if I can begin with an inequality of two functions like this, I will be able to transition to the definite integral. So this is how I plan to get my inequality. So the one that I need to have an inequality, some statement about f and g. You can imagine, for example, that this plays the role of f of x, let's say, and this plays the role of g of x, something like that. Okay, so then let me begin with a true statement, something that no one can question. We are dealing here with the interval 1 to 4. So that's my interval from 1 all the way to 4. I know that in this interval, x is greater or equal to 1, right? Nobody can question that. In the interval from 1 to 4, an x value in that interval is going to be greater or equal to 1. If I now multiply both sides of the inequality by a positive number x, then I am going to get that x squared is greater or equal than x. Equivalently, that means if I take reciprocals, that 1 over x squared is going to be less or equal than 1 over x. And again, all of these x's that we're dealing with are in the interval from 1 to 4. So this is true in that interval. So all of a sudden, I already have, again, imagine that this is f of x and that this is g of x. What I have here is that f of x is less or equal than g of x in the closed interval 1 to 4. Which means that I have already achieved the inequality that appears right here in the condition of my property. All that I need to argue now is that f and g are integrable in the closed interval 1 to 4. But this is not too difficult because look at this. I know that f of x, which is equal to 1 over x squared, and g of x, which is equal to 1 over x, are both continuous in the closed interval 1 to 4. So that implies, if these functions are continuous, that implies that f of x and g of x are integrable. Integrable in the closed interval 1, 4. And this is by theorem. So now that I have satisfied all of the conditions of this property right here, I can perfectly now claim, I can say, therefore, the integral from 1 to 4 of 1 over x squared dx is going to be less or equal than the integral from 1 over x dx. End of proof. I know, however, that some of you will be thinking, oh my goodness, I would never, though, have thought about starting with the statement that x is greater or equal to 1 in the closed interval 1, 4. I know, I get it. Sometimes it is a little bit tricky to think about this type of true statements, even though it's so true, so obvious, may be difficult to think about that. So another way that you could have started thinking about this relationship or this inequality is through a graph of what you really have here. Here I have x and y, and I'm going to go ahead and graph x squared and x. So I know that y equals x will go exactly through the middle right here. This is y equals x. And then I am going to have y equals x squared. And they will both intersect at the point 1, 1. So x squared is 0 at 0. It is below the line as x goes from 0 to 1. And then x squared overpowers the line. It goes completely above that value. So then please look at this right here. Here is where they intersect. And then as soon as x is greater than 1, as soon as x is bigger than 1, or in other words, if I focus on the interval from 1 to 4 right here, I want you to notice how x squared is completely above y equals x. X squared is above x. So then, just by looking at the graph, you can convince yourself that indeed x squared is greater or equal than x in the interval from 1 to 4. And then that means taking reciprocals that 1 over x squared is less or equal than 1 over x. And then as soon as you get to that point, then notice that everything else, the argument is the same as before. You're going to argue that 1 over x squared and 1 over x are continuous, so they are going to be integrable. And then you can go ahead now and conclude exactly that the integral from 1 to 4 of f of x is less or equal than the integral from 1 to 4 of 1 over x. So there are two different ways that you could have gotten to this inequality right here. In this last example here, they're asking us to prove another inequality. They're asking us to show that this definite integral is between 3/4 and 3. And I plan to again use the comparison test properties for integrals. I want you to notice how in the integrand we have 1 over x. So that becomes the function. In other words, f of x is equal to 1 over x. This is our function. In the interval from 1/2 to 2. And I'm going to quickly draw a rough sketch of this function in my interval. This is x, this is y. And in this interval from 0 to positive infinity, 1 over x looks like this pretty much. It approaches the y-axis asymptotically, and it also approaches the x-axis asymptotically. So we are going to have 1/2 somewhere here. Let's pretend that here we're going to have 2. So we are looking at this point on the graph when x is 1/2, and we are looking at this other point when x is 2. In fact, let's calculate f of 1/2. F of 1/2 is going to be 1 over 1/2, which is 2. And then f of 2 is going to be equal to 1/2. And I'm going to write that down over here. This is going to be 2, and this is going to be 1/2. What is really obvious is that this graph is a decreasing graph in the interval 1/2 to 2. So then in that interval, 2 becomes the absolute maximum, and I'm going to make a note of that. This becomes an absolute maximum in my interval, and 1/2 becomes the absolute minimum in my interval from 1/2 to 2. So then what I know immediately is that my function 1 over x is going to be greater or equal than 1/2, and is going to be less or equal than 2. So practically then, I found a lower bound and an upper bound. In fact, 1/2 plays the role of little m, and 2 plays the role of big M. And therefore, I know that when I find my lower bound and my upper bound, it follows that the integral from 1/2 to 2 of 1 over x dx is going to be less or equal than 2 times 2 minus 1/2, and greater or equal than 1/2 times 2 minus 1/2. So then the integral from 1/2 to 2 of 1 over x dx is going to be less or equal than 2 times, that is going to be 2 times 3 over 2. And then over here, this is going to be greater or equal than 1/2 times, again, 3 over 2. So then this is going to be, or this is going to say that 3 divided by 4 is going to be less or equal than the integral from 1/2 to 2, 1 over x dx, less or equal, notice over here that 2's cancel out, less or equal than 3. And this is exactly what we needed to show. I also want you to notice that all of the functions that we're working with in here, the constant functions 1/2 and 2, those two functions are continuous, so they are integrable in the closed interval. Similarly, the function 1 over x, look at it over here. It is continuous in that closed interval. So if it is continuous, it is integrable. So the conditions of the properties are completely satisfied. So if all the conditions are satisfied, then this conclusion is exactly true. And that's the end of the proof.